In this video, we're going to go through what the definition of perpendicular lines are and then two theorems which are related to perpendicular lines. So let's start with what perpendicular lines actually are. Perpendicular lines are basically two lines which, when they intersect, form right angles. So let's get a diagram to visualize what that's representing. So in this situation, line L, this line, and line N are said to be perpendicular, which is represented this way, L perpendicular to N. This is the symbol for perpendicular. If and only if, which is a biconditional statement, they are intersecting to form right angles, which would mean that angle 1 would be a right angle, so would angle 2, so would angle 3, and so would angle 4. So all four of those would be right angles, but if I label just one of them, it's enough to represent that information. Now it also means, because of this definition, that if I know any of these four angles are right angles, I could also conclude that the two lines were perpendicular. We'll see examples of how to use them later in the video. For now, let's look at our first theorem, which says that two lines are perpendicular if and only if, again, another biconditional statement, they form congruent adjacent angles. So what that theorem basically says, two things. The first is that given lines are perpendicular, then I can conclude that the adjacent angles are congruent to each other. And second, the other direction of that biconditional, if I have congruent adjacent angles, then I could conclude that the lines are perpendicular. So this theorem goes in both directions. We're going to look at both directions and how to actually prove this theorem, because remember, all theorems in math can be proven based on information we've already seen. So the first part of this proof is basically this direction. Given that two lines are perpendicular, then I can conclude they form congruent adjacent angles, is what I'm going to show first. So given the lines are perpendicular, line L and line N, I'm going to prove that angle 1, 2, 3, and 4 are all congruent to each other. So the proof for that is right here. And what I want you to do now is pause this video and see if you can fill in what the reasons for these three statements are going to be. It's a rather short proof, so I just want to see if you can see what these reasons are. So pause the video now. Okay, so the first one should be obvious, it's given to me. That's the hypothesis of my theorem. Secondly, angle 1, 2, 3, and 4 are right angles. Well, that's not blatantly obvious, but recall we just went over what the definition of perpendicular was, which says if two lines are perpendicular, then they intersect to form right angles. So since I know those two lines are perpendicular, L and N, I can conclude that each of those lines, from those lines being perpendicular, I can conclude that each of those angles are right angles, and that's the definition of perpendicular. So that's one way we can see that definition used in a proof. And then the third line, angle 1 is congruent to angle 2, is congruent to angle 3, is congruent to angle 4, is actually a theorem that we've talked about but haven't used in a proof yet. And that's the right angle theorem, which says that all right angles are congruent to each other. Since all four of these angles are right angles, they are all congruent to each other by that right angle theorem. Okay, so that was the first direction of the proof. The second direction is the other part of that biconditional, which is going from if I have congruent adjacent angles, then I can conclude that they are perpendicular. And that's what this second part says. Given a set of congruent angles, so knowing that angle 1 is congruent to angle 2, given that information, I should be able to prove that line L is perpendicular to line N. So taking a look at that, what I'd like you to do again is pause this video and see if you can fill in the reasons to this proof. Okay, the first one again, given. Usually in proofs in geometry, we'll start with given information or information which we can pull straight from the diagram. Now the second step actually doesn't follow from the first, and that is information I'm drawing straight from the diagram using the angle addition postulate. Angle 1 and angle 2, since this is a straight line, when added together, will add up to be 180 degrees. The second step is actually kind of two things happening at once. First, if you notice, let me highlight it so you can see it a little bit clearer. Since the measure of angle 1 is equal to the measure of angle 2, I can replace the measure of angle 1 with the measure of angle 2 at any point in time using substitution. And then I'll have the measure of angle 2 plus the measure of angle 2, which I could more simply write as 2 times the measure of angle 2. So that's really a substitution property. I'm substituting the measure of angle 2 for the measure of angle 1, adding them together, and that's what I get here. The next step, I'm taking that 2 from equation 3, and I'm dividing both sides of that equation by 2, so that I get just the measure of angle 2 equals 90. That's using the division property of equality. And once I know the measure of angle 2 equals 90, that is by definition a right angle. An angle which measures 90 degrees is the definition of a right angle. And once I know that angle 2 is a right angle, then by the definition of perpendicular, I know that those two lines are perpendicular. Recall the definition of perpendicular says that two lines are perpendicular if and only if they intersect to form right angles. So since these two lines intersect to form right angle 2, we can represent that visually in the diagram. These two lines, L and N, are intersecting to form a right angle at the angle 2. Then by the definition of perpendicular, they are perpendicular to each other. So that's two ways that we can use definition of perpendicular in a proof, and we've actually used it to prove this new theorem, perpendicular if and only if they form congruent adjacent angles, and we can now use this in proofs, and we'll see examples of how to use this in proofs in class tomorrow. The last theorem we're going to talk about in this video is if the exterior sides of two acute adjacent angles are perpendicular, then these angles are complementary. Recall what it means to be an adjacent angle is an angle which shares a common side. So angle 1 and angle 2 here are said to be adjacent because they share side OB. So that makes them adjacent, sharing a common side. And what this theorem is saying is that if the exterior sides are perpendicular, so given the fact that these exterior sides are perpendicular, so that would be that OA is perpendicular to OC, I can conclude that these two things will add up to 90. And if they add up to 90, then by definition, they're complementary. So rather than going through that sequence of arguments, we can use this theorem in an example to go straight from the fact that these two exterior sides, which are the sides which the two angles do not share in common, these exterior sides are perpendicular, to the fact that they are actually complements of each other. So angle 1 is complementary to angle 2 for this reason. So rather than go through this whole proof, and it can be proven, this is an example of how you would be able to use this theorem in a proof, and we'll look at more examples of it tomorrow as well.